So this is challenge 5 for protostar, where we need to uh, solve this one. So let's see the code of the challenge 5, which is saying that this is a standard overflow, and this time we need to actually execute our shellcode within the system. And so let's get started with the code. And so looking at the code, it seems like there's a main function, and then it accepts an argument, and there's a buffer of 64 bytes, and then later on it's being fed to get function. So this is a classic buffer flow where you are supplying 64 bytes. The program expecting a 64 bytes, and you will supply more than that. If you will supply more than that, then it will reach into buffer flow. Why? Because get function doesn't do a boundary check, due to which you can basically supply more than the expected value by the buffer. So let's try to do. We will be first try to load into GDB, and we'll see like how we can get a shell out of the system. So for that, let's run the program and see how. So basically, it takes input, and I will try to supply A here because um, it's similar, like it's familiar to understand. Like okay, for the A value, what is the hex value in the memory? So let's see. So it exits up like after accepting the value. Let's try to load it into GB before that to understand the step 5, and let's set the disassembly flavor to the Intel. Now just disassemble the main. So this is the previous EBP is pushed into the stack, and then stack frame has been set. EBP and ESP are pointing at the same location. Some adjustment, and here stack has been subtracted with x50, which is to reserve some space for the variables. And here we are taking some value from actually like the value stored into EAX from this location because it's indirect referencing. So basically, it's a movement of value. And yeah, there's some. Finally, after this, the gets call is being called, and then finally execution. So we'll try to set certain breakpoints to understand what's happening during the execution of the program. So I will try to I like to set breakpoint at the leave instruction, and let's run our program because I've set the breakpoint after the gets call has been done and I've finished execution, because after getting the value from the user, um, it will be returning up, and we wanted to analyze the state after that. What's the current scenario of the stack? So let's run this program, and I will try to supply like A here. The more A better, by we'll see, and we hit the breakpoint. Let's analyze the first basic fix in the hex data 50 hex portion of the ESP. Yeah. So presently you can see like our stacks, our buffer starts from here because we can see that our supply data, which is A, is generally in hex it is 41. So we can see that from here we have started overriding our data, and this is the start of the buffer. So fine. So the main goal of this challenge is to actually execute, should be able to overflow the buffer, and you need to override the EIP instruction, EIP register with R value, where we will be hosting a malicious code which will finally get us a shell within the system. So to do that, like first we need to understand like how many exact amount of data, or let's say characters or bytes we needed to actually overflow, or let's say to reach out to the EIP. So for that, what I can do is like I have one program I generally use this. We'll create a length of 100, a string of 100 length, and basically it gives us a basic, you can say, a payload. This is similar to Metasploit pattern where basically you generate a pattern of, well, let's say, a particular length, and then based on that it calculates and gives you, okay, what was the actual memory where it was, where it was the error, or let's say seg fault, and based on that you can calculate the actual error. So we'll see. So let's try to run this program with this payload. So I'll just rerun the program, and this time, so we hit our breakpoint, and let's continue the program for this moment. And we saw that, hey, for the 100 length of input, we actually hit the seg fault. Basically, this is happening because the 63, 41, 35, 63 is not valid, address which CPU can point towards. So because of which, we got a seg fault, and this address cannot be, resolved. So by this way, what we know is we were able to corrupt, or we can say we were able to overflow our buffer and finally reach out to the EIP as well. So we basically overflown it, and now we need to analyze it. Okay, whether it was actually, we actually overflow or not. So, but our first of all problem is to basically analyze how many actual offset we need, or let's say padding we need to reach to the EIP. So let's put this value here, and based on this current address, it will calculate the actual amount of offset which is needed. So right, it says like 76 bytes are needed to actually reach out, to reach out to the EIP. So let's try to, validate the same. So I'll be using, I think, for let's say 76 bytes, 76 characters we can give, and sorry. So we need to give print as well to print the values, and just read in the program with our current data. And let's analyze the stack at this point of time. And what we see over here, since our buffer starts from here, we are able to overwrite uh, 76 bytes which of A, which is supplied basically till our buffer is starting from here and it indicate here. And what it means, basically, the next 4 bytes, since if you see how the stack is laid out, is like the first, it will be a buffer, and then post buffer has been overfilled, there will be the value of EBP comes into picture, and if you override in the EBP, then after EBP there will be EIP, or let's say, the EIP is EIP register, and this will require, let's say, since we're able to overflow till 76 bytes, to reach out to the EIP, we need extra 4 bytes. Why? Because it's a 32-bit system, and every address, you can say, word of it will be like, so this is like till 76, and then to reach out to the EIP, which is, at this point, we need to add 4 more bytes into it to override the EIP. Why? Because it will be 4 bytes ahead of the current address. So why we are sure about this? Because let's say, let's try to give the same payload, or let's say the same string which we gave earlier. Sorry, yeah. Now, if at this time, if we try to examine the stack, you can see we supplied 76 A's, and here we supplied the same 100, a length pattern. So since we know that this is the address where a stack started, till here, let's say, which is like 70 A70 70 till here, this is our place where our buffer ends up, and post which, since the CPU gave error, let's say, at this address, because segfault happened at this address, it means that we have overridden the EIP, the return address, you can say, and now since it's not a valid address, the CPU will give it segfault. So this is basically was overridden at the EIP value, and by this we know that, okay, this will be the EIP of the present code. So basically, after the 76 byte, we just need 4 more bytes to actually overwrite the EIP. So for just to check here as well, if you give continue the execution of the program, you'll get a 6 fault. Yeah, and at this point, if you want to analyze the CPU or let's say registers, you'll get the IP is pointing towards the same, which we validated. Now let's try to check whether this is true or not. So I'll just add like 4 more bytes to it, and we get one more pattern. Let's apply this input to the program. Let's rerun this, and let's try to continue that. We got to know that 4 to 42. Now the sec fault is at this address. It means we were able to overwrite with B's, like 4 B's. So B basically in hex, if we know about it, it is 42. So it is clear that we are able to override the EIP, we were able to control the EIP. Now the next step is to actually point EIP to such an address where your malicious shell code or your code lies in, which will be doing further step for you. So what is the shell code? Shell code is just a piece of a code which does a particular operation, which can be act as a payload once you control the execution flow of the program. So payload in the sense like you can give a particular set of instructions. Let's say execute a calculator, open a port, or you can even simple execute the shell. So that's a piece of code. Generally, it is written in assembly. Then basically for our purpose, I've converted it into hex, so that it's easy to contain. So let's go to exploit for this, and we'll discuss the general approach for this. So now how we can execute, since the challenge says we need to execute a shell. So I'll be writing a stack. You can say 5 new.py. So basically the Python module we are writing up Python code. Now we just need the first offset. So we know that we need 76 offset to, or you can say padding to actually reach out to the EIP just before the EIP, and the next 4 bytes to actually overwrite the EIP. So I'll just type EIP, and I'll just for the moment I will fill it with a B, and that our shell code. And let's offset, that's EIP plus shell code. So pretty much the same. Pretty much what we are doing is we are reaching out to our just before the EIP, and then with this value we are actually overriding the EIP, which will point to our malicious code, which we'll be injecting with the help of our shell code. And finally, when once the program has reached to EIP, and since we need to fill it with the valid address where we want to jump, and this valid address should be pointing to our shell code, which will finally execute the code which we are intended to execute within the system. So we need to figure out where to jump exactly, and before that just need to fill this shell code. So I'll just save the file, and I have already saved the shell code, which is, you can get it from shellstorm.net or .com, where basically this specific shell code, what it does is basically execute or gives you a shell. So I'll just copy it exactly, and then let's say stack 5 new, and just fill up here, and yeah, so we have a shell code here. And so we need to figure out like what's the exact address we wanted to jump before where our shell code will be, and where we want our EIP to point. So if we remember that, we know that our buffer starts from here based on the previous data. So we can give this value as well, so that once the EIP has overwritten, it will come back to this address, and since this address will be filled with our shell code, then due to which the CPU will start executing this. So let's try to run the same. So let's see what we can do, or more better than that, what we'll do is let's rerun the program. I would prefer to get the actual symbol address of our buffer from the program itself. For that, that's fine, we hit our breakpoint, and just wanted to figure out the actual buffer address from where our buffer is starting at the code, rather than I will preferring this, because since the system is not having any sort of protection right as of the moment, which is enabled like ASLR or NXPED. So what's happening here is like each time a program gets executed, it will be loaded in the same address. Means each and every variable, or let's say a library, will be loaded in the same address, static address. So right now it's a static exploit. It will become a challenge when other system level protections are on. So it's better like if I give EIP this address, what will happen is like the moment EIP is hit and overridden with this, EIP will jump towards this buffer, and finally, since we will be injecting our shell code, uh, finally it will get executed. So let's copy this address, and let's try to paste over here. So since it accepts in Little Indian, we need to reverse this. So yeah, what we are missing, yeah. So let's try to execute this first, and so it says A is not defined. Okay. Oops, that's a mistake. Should be in count. In yeah. Orchestra. Yeah. So nothing happened. So what was the reason is because we are placing our shell code directly. It's possible because might be our shell code got truncated, or it doesn't land up in the proper address. So to handle this, we will add knob sled, which will be so x90 means a knob, in hex, and what it does basically, it tells CPU to do not any sort of action. It just tells him to basically implement the IP. So go on and go on till it is being instructed. So I'm giving 90 knobs. So we call it knob sled. Why? Because once the offset we reach to the EIP, we have successfully overridden the EIP. We need to reach jump to that as well. Shell code is located, but sometimes because of either loading of the program in different environments, that is and other factors will come into picture where the address space, or let's say address, might get changed. So due to which our shellcode will not be properly, or EIP won't be properly pointing it to shellcode. So for that, to ensure that our jump happens, properly, and we reach out to our shellcode, we will inject, or let's say we will add knob sled. So basically, after the EIP is overwritten, then knob sled will give enough, it will be act as a ladder to our shellcode. Why? Because it will instruct CPU to take no action and just keep on going until you hit our shellcode. So basically, it adds up reliability for the system, which we're going to see now. So yeah, I think that should work now. And yes, so we got a shell system. Since it's SUID, so you can type, yeah, should be root. So that's pretty much.